That is actually too much. Is why it is showing like this. I'm just going to write as 10, maybe if anything. It is just going to show the pixels. There are 784 divisions of one pixel. Okay, so you'll get 784 input layers. Sorry, 784 inputs in one layer. 784 neurons you can say. There is one layer, there are 784 inputs coming to the hidden layer. Okay. Now normalizing input data. So we use this normalizing input data. So because we want all the values to be adjusted between 0 and 1. So it's easier for the machine learning algorithm to understand that data. And when we are doing this kind of normalization, so because it is all relative. So let's say something is zero point 0.9 and something is zero point 0.6. So in other kind of other scale, it would be some one should have the range from 1 to 1000. Some will have the range from 1 to 100. So it is very difficult to do that. So we are normalizing it and making it. And so right now we are taking from range from 0 to 1. You can take from other perspective also. You can take from 0 to 10 and anything based on your requirement. So we are normalizing the input data for so that our machine learning algorithm does not get confused because of the diversity in all the pixels, all the inputs. Whatever the diversity the pixels have or any data have, that would not affect the result. That is why we are using this normalization, and we are putting those pixel values between 0 is going to show like this one. This is the text in multi-dimensional array that you're getting. So now this is about the the pixels. Okay. What about the result? So we know that this is the label data. We are learning from that label data. So there has to be some comparison also. There has to be some comparison so that no, okay, I have read this vector. Now, what do I learn from this pattern? Okay, that it is one. I have read second vector. What do I learn from this whole pattern? Okay, because it is image with number two. Okay, it is digit two. All right. So we need to convert those now those labels. I need to convert in one hot encoded vectors. What are these one hot encoded vectors? Let's say I'm saying the outputs. Okay, therefore I'm doing the classification problem, right? So I'm taking one input, I'm classifying it, which category it belongs to, whether it is zero, whether it is one, or and so on, whether it is nine. Okay, so 0 to 9 we are actually classifying. So every single class we are going to uh, give a one hot encode into that much dimension. Let's say there are four classes. So we will make a binary equivalent of four digits. Okay. So let's say 0, 0. So we will represent 0 as 0, 0, 0, 0. Okay, 1 as 0, 1, 1, 0, 0, 0, 1. So it is does not mean that it should be a binary equivalent of, it will be a binary equivalent of 1. Okay. So it does not mean that it will be binary equivalent of that. Okay. So the thing is, we are going to hot import and it will change that. Let's say I have 9. I have, let's say, 5 classes 0, 1, three, four, five. Okay, so when I'm not encoding it and I'm writing five, let's say, so it will be like this. Um, you just need to write it as I equal to. Okay, so it will be like something like this. We have six classes, sorry. So we have six classes here: zero, one, two, three, four, five. So that is what we have to do. Okay. Now, if I'm saying that this is five, nothing. If I'm saying that one, double zero, and triple zero, this is five, then four will be something else like this. Maybe four might be like this. So one will be at one place only, not multiple places. So we're just making a differentiation so that every category is different, nothing else. So that is what we're doing here. We're making one not included target variables. See this 0, 0, 0, 0, 0, 1, 1, 0, 1. So they're both different categories. I think one hot encoding as this one hot encoding is clear. Is there any confusion? You can ask. So this is important, and you'll have to do it. You have to make, you have to make that classification. You have to convert it into a vector. Okay, the whole classification labels, you have to convert it into vector, and that is what we are doing here. We are making it a one hot encoded vector, and every vector will be different. Right? So far what we have done, we have imported the libraries, we have loaded the data, we have reshaped the input data and made it a vector. Okay, you know, dimensional vector, 1D vectors is array of 1D vectors. And then we have normalized the input data and we have converted our that target variables or the labels into vectors again, different vectors. That is why we actually imported this library. Okay? Categorical is actually doing that job. Now we are going to design our neural network. Okay. So neural network, how are we going to design? First of all, we are writing model is equal to sequential. What does it do? It does nothing, but it creates an empty neural network model. So okay, this is the empty space, and here I'm going to make a, our neural network model. So basically, treat it as like in class, you are supposed to create an object of the class. Treat it as the same way. I'm creating a model and I'm creating when I'm writing model is equal to sequential, I'm creating an empty neural network model. Now, in this empty neural network model, it is up to me to add the layers, and I can add as many layers as I need. Okay. So right now, after that, what I will do, I've created this, I've created an empty neural network model. All I have to do is create, means sorry, add layers. Okay. So of all, I need to create an input layer. Okay, this is my input layer. Model dot add dense 512 input shape 784. So now when I'm saying dense sense 512 means that has 512 neurons. Input shape 784 means that means that means the first layer in the model, it expects the input data with 784 features. Okay, 784 features it will accept. It will expect. Okay, there I'm writing this activation value. So you don't know that, okay, in for neural network, we need that activation function also, right? That is what actually is doing all the things. Okay, so any changes is going to make, we are doing to use rectified linear unit. So what is rectified linear unit? It is nothing but when it is when the value is negative, let's say, it will change it to zero, and when the value is positive, it will give as the same value. Okay, so it is max, zero, and value. Okay, but while either it is zero, so even so basically what it is doing, it is diminishing the negative values to zero, and the positive value is going to keep it as intact. That is what it is, rectified linear unit is doing. Okay, so what is actually it is doing? It is introducing non-linearity to the network. So in linear regression, we know that we are actually learning through a linear model. In this, we are not just learning a linear model like x is equal to y, x is equal to my or anything. Not like that. We are going to learn the non-linear patterns. Okay, we're going to learn the non-linear patterns, and we're not going to actually. The machine is going. The model is going to learn the non-linear patterns, and that is why we are using this activation function as REL. Okay, so it will convert our, as I said, max, zero, and value. I think I have written it somewhere. Ah, yeah, see this. This is the formula for uh, this rectified linear unit. So because of this, our machine is able to learn the non-linearity, okay, non-linear functions, non-linear. So when we are dealing with a complex problem, if we go through the linear data, that is not sufficient. So we have to read the non-linear patterns in the data. After that, what? So I have done this. Then I'm adding the dropout layer. So dropout layer means nothing. To prevent overfitting, we are doing dropout layer. So what is dropout 0.1? So what it is, maintaining a probability that for every neuron that is passing, there is a 10% probability. When I'm saying 0.1, then when I'm saying 0.2, then it is 20%. So when I'm saying dropout 0.1, for every neuron that is passing, there is a 10% probability that it will be dropped. Okay, that's it. So it is not a total 10% probability, or you can say, okay, 1,000 of them are passing, only 900 of them will be passed. Okay, it is just a probability. It's a 10% probability that particular neuron will be dropped. Okay, so every time it creates a random effect, and every time it is this the neurons, the number of neurons are random. So that we did. Okay, so we had this input layer and the first tense layer, and then this is where we have the dropout layer. Okay, now what? Now we have this hidden layer. Okay, now the hidden layer, that is 512 neurons, and again activation rectified linear unit. Okay, so now in this again we have an activation function, that is rectified linear unit again. So we have a hidden layer. In this also, in this layer also, it will learn the data. So it got some input, it will create an output. Again, it has to create an input for the output layer. Okay, so for the output layer, this is the hidden layer is the input layer. That's what we discussed actually in the previous class. Not much that is how neural networks work. The hidden layer is now the input layer for the output layer. Okay. Now again we are dropping making the dropout as 20%. So there's a 20% chance that a particular neuron will be dropped. Okay. When I increase that dropout, then obviously the number of dropouts will drop neurons will be increased. Okay, but it is not, again it is not assured that half of them will be. drop. Okay. So after that, what I'm seeing, okay, these are the 500 to 12 neurons activation review, and I'm dropping out the 20%. I'm putting that 20%, dropout, 20% probability of dropout. And after that, you are seeing that model dot add. So when I'm writing this model dot add, that means I'm adding a layer. Okay. When I'm doing this model dot add, 10 activation software. This is where we are actually creating our output layer. Okay, this is where we are creating our output layer. Why it is 10? Because we have 10 sets of output. Okay, it can be one, two, three, so 10 categories we have, right? That is why we are doing this. Okay, and what is this softmax function? Okay, what why we are writing max function, why we are doing that. So the thing is, whenever we are actually getting an output, so we are getting 10 features of that. I will just write something here. So let's say one feature is saying for the output being 0, the probability is 0. For the output being 0, the probability is 0.005. Okay, for the output being 1, the probability is, for the output being 1, the probability is 0. Let's say 0.7, 0.75. For the probability being 2, the for the digit being 2, the probability is 0.08. So every category, our output will have some kind of probability. Okay, because of this sort math function, it is just going to give the probability, and the highest probability that it has, that will be output. Like in this, I can say, okay, the one has 1 category has 0.75 probability, so this is the answer. Okay, so that is how our soft function is going to work. So, basically, we are making a comparison. Okay. So we are giving a relative data, relative output, probabilities, ensuring the sum of the all the probabilities should be equal to one. That because some will be 0.08, so it should be equal to one. All of them should be equal to one. So after this, after when this is done, let me after when this is done, we are going to compile a model. Compiling model means what? And then we are going to train it. This is dot fit. So what is the difference between compiling and actually training the model? Let's say you want to go to gym, but before going to gym, you have to go to the before actually going to train in the gym, you have to going to take some you have to make some preparations, right? You have to set up the gym. You have to see, okay, these are the machines I'm going to work on. Okay, you'll have to make a plan, everything. After you have made the whole plan and you have created the whole setup of that gym, let's say you're training at home. So you actually come and, I have created one bench press machine. I have actually purchased one bench press machine, set up that, and I have brought some dumbbells and everything. And I have made the whole setup so that my training can be started. So that is compilation. When actual training, your actual training starts when you actually start to train. That is your fit method or training. I think that is understandable. So if there is any question, you can interrupt me and ask. Basically, that is what we are doing. We are actually preparing the model, and then we are training. In the preparation of model, what do we need? We need the loss function, we need the optimizer, and we need the metrics. So why do we need the loss function? Loss function is nothing but it indicates the difference between your calculation, whatever output you have created, and the reality and the label. Okay, so if the loss function is more, means you have some problem. That means you need to correct some problem. Now, optimizer Adam optimize as an Adam, this is an inbuilt optimizer, so that whatever learning it might have, it will always be dynamic. Okay, every time it will make a dynamic learning rate, and it will the learning means what? The change in weights and biases, and the matrix here will always calculate the accuracy. Okay, that is what it is saying. So input layer 784 neuron, dense layer 512, dropout layer 20% dropout rate, and then dense layer, this output layer. So this is what we have. This is our neural network. So now we are going to compile the model. We have created our model. Now I'm going to train our model. Epochs 10 means again batch size 150. Let me take it as 128. Now it is calculating the loss, also calculating the accuracy. So in first epoch, we are saying, okay, this is the accuracy, and this also loss. So see, now accuracy is increasing as the neural network is learning more and more. The accuracy is increasing. And in every epoch, epochs means I have taken epoch 10. You want, you can take 5. If you want, you can take 20. It is to the extent I want to train my machine. So if I would have done only 2 epochs, I would have done 89 and 75 accuracy. So in every epoch, the whole data is going to be passed through the neural network. Okay, then that data is being, we are adjusting the weights and biases, and again that data is going to be in the next step, in the next epoch. Again, that data is going to be entered with changed weights and biases, and again we are going to when we are going to produce a result. Right now, see that the last one accuracy is 0.9. It's pretty good thing. we're getting an average accuracy. If we are getting, we are testing this as test by test. We are getting this accuracy 96.9. So this will conclude our lab one. Are there any questions? Not, then we'll move to the next lab. Our next lab. So experiment number two. Design a neural network to classify movie reviews, binary classification using IMDb dataset. Okay. Now in this, we are going to analyze that text and see whether that review is positive or negative. Okay. How do we do that? Again, you are going to use neural network. So whatever I have told, I'm not going to like repeat concepts. And the conceptually, what is synonymous? Only that. Okay, so this is the upgrade thing. If install upgrade TensorFlow, if you want to upgrade, you can. So what are the libraries that we are going to actually import the IMDb? So we want data sets, right? So right now we don't have any data in our folder or anything. So we are going to take the data sets from Keras. So this is a practice problem. So that is why we are taking. So you might have your own set of data sets and you can work on that. Okay. Whole point of taking this data set is to save us the trouble of creating the whole data set. And maybe data sets. And again, we are taking sequential dense and dropout to create the layers of neural network. I think so far that much is clear. And you will see the use of this add sequences. So again, same way, we are going to load the data set and it is already being already divided in test and training set. We don't need to divide it again. Numbers 10,000 that you're saying is we are making the vocabulary size to 10,000. Okay. So 10,000 unique words can be there in one, uh, you know, one data, one rip. Okay. Unique. So that is what it is. So we have to reduce the dimensionality. So we are taking okay 10,000. So now there are I know that there are 100,000 words in the English alphabet, or even maybe even more. Okay, but we are limiting our vocabulary size to 10 because our system has limited uh, capability, and then there is also the time comes. Okay, so let's say I'm taking this. I've got this data. I have downloaded the data. Now, this paired sequences, as I talked before, we're talking before, we are importing paired sequences. Why we are actually importing paired sequences? We are going to our everything that we are getting. We are giving a maximum length of 200. Paired sequences does what? It is actually making the whatever I'm getting, whatever input I'm getting, it is giving at it is making all the inputs uniform, making it 200 words. All the inputs making uniform. So there are uniform inputs in like if there are uniform inputs, it's easier to machine to interpret. Now we have taken this maximum length as 200. That is how we're going to be defining the model. Okay. Again, now we are defining the model. Model is equal to sequential. Again, creating a new empty neural network. we discussed before. Now we are adding here hence 128. So now 128 neurons. Again, we have this ReLU function, and input shape again will be max length. So there are 200 words, let's say. So all those are inputs now. Now we have an input shape of 100. So the first layer will be expecting the layer will be expecting the input of 200 units. Okay. So here we are actually what we are doing. We are giving a little bit of layman language here. So let's say we are adding a layer to our neural network. Think of it as a room with 128 light bulbs. Each bulb, a neuron, can be turned on and off. When we turn them on, they pass along the signal to the next leaf. Okay, that is what it is doing. The ReLU activation function makes sure the light bulbs only turn if the input is positive. As we said, this is our ReLU function. Okay, rectified linear unit. So whether only when it is positive, you'll get when it is positive, you'll get you know will get a signal, or when it is negative it will give zero. That means will not turn on, it will not pass. Okay, the input shape tells the model the size of the input data it should expect. That's what I said, 200 with the size of the input. All right, so why we are actually using this dropout again to prevent the overfitting. Okay, so when we are training the data, when we are training our machine, sorry, when we are training our machine or model, we are training on particular features. We are training on a lot of features, let's say, and we are training on true matrices. Okay. Now we don't want that our machine overlearns. Okay. When if it is overlearning, our machine is overlearning, then it will give the desired output only on the training data itself. When it is getting the new output, it won't be able to get because it is so much. It has to learn so much through the training data that if it doesn't get the exact thing, it won't create a output. It won't create a desired output. Okay, so that is why we are using this dropout so that overfitting must be avoided. Now we have this dense layer. Again, we are adding another dense layer after the output so that new complex patterns can be understood. Okay. Again, we are putting to the out. So now again, this is let's say input layer, then hidden layer, again a hidden layer, and again the last hidden layer is again the input layer for the output layer. So again, we have the dropout. So neurons that are going, there's a 50% probability that they will be dropped. Some of the neurons will reach, and some of the neurons will not reach. So now this is our output layer. And why does it have only one? Because either it is positive or it is negative. So we need only one. Why? Because whatever the probability might be, let's say it is 0.65. So it will be considered, okay, it is closer to 1. Okay, then it is 1. 0.3, okay, it is closer to 0, so it might not be the desired case. So it is 0. Okay, then the review is negative. So there is no absolute 0 or 1. We are getting the probability of the comment or the review, how much probability of that review is being positive. So if it is being positive, let's say the review, the probability of review being positive is 0.8. That means the review is positive. The probability of review being positive based on the learning of the machine is 0.2. That means can be negative. Most probably it's negative. Now again, so I've told you why we are using this model.compile. Again, we are doing the same thing. Here we are taking binary cross entropy. What we did, we take there categorical cross entropy. So here we are taking categorical cross entropy. So there are different categories. Here we are taking binary cross entropy because that is what we need. Okay, optimizer is Adam itself. So they are predefined optimizers or loss functions. Now we are using this model.fit. Again, we have taken this box as penny box. Okay. Right now, we are seeing that accuracy might not be that good, and it is not actually behaving in the way we want. So, in the last, we are getting 50% or something as accuracy. That means there's not much improvement as we were actually hoping for. Okay. So, there might be a reason that would be some shortcomings in our algorithms or neural networks. We have a similar lab to improve this algorithm, and we will get a higher accuracy. But that is actually there's an algorithm after this. I think experiment number experiment number. I think it's in the last. So we have that, and we will go through that. Okay, so right now it's a preliminary algorithm, you can say. So right now we have a accuracy of 50%. That is not a good accuracy, and I know that. We will go to some advanced algorithm. Accuracy being 50%, even after adding these the neural network and the layers, and using this binary cross entropy and everything in optimizer Adam, we have done all that. But even then, we are not getting 50% algorithm, 50%, more than 50% accuracy. That means our our whole data is complex, and we need a complex algorithm to actually make our machine learn through that data. We will do that. Okay, most probably tomorrow. So this will conclude our experiment two. Are there any questions? So we are going to move to experiment number three. That is designing a neural network for classifying news wires, multi-class classification. Okay. So here also we are making a classification. So basically, when we are doing that, we are again importing this to category. So let's say this, we are importing necessary libraries. So right now, we have this default, and we'll see why we are doing that. I think it means it is data set. From this, we are getting that Reuters data set, and again we are taking that vocabulary limit of vocabulary to 10,000 words on. Don't worry about this one. Now, when we imported these libraries, I'm loading the data set. Same way, we don't need any division. It is already being divided in training and testing. Let us dot load data. It is working. Now we have the data. Now we are going to vectorize the data using one hot encoding. So this is actually a function for doing that. Okay. So we'll come to this later. I'm running this, that whenever I call this function, they should actually be available. One hot encoding is a technique used to represent categorical data. I've actually explained to you how we are actually using that one hot encoding, how we are actually differentiating the categories using a binary sequence. Okay. So right now we are using this xtrain and xtest, and we are vectorizing the sequences. Means we calling this function vectorize sequences on this xtrain and xtest. So what is happening in this? Sequences dimension 10,000. So it is creating an array of zeros and with the dimension of 10,000. Then what we are going to do for I sequence this, return results. So let's say I am going to, you know, just write this, have some, going to write only five. Every time this needs to run so that you can see 0, 1, 1, 1, 1. And that has been, this has been vectorized now. So basically what we had in our X train and Y train, we had some words, right, in the set of words. Now we have made it in the form of vector. All those words and sentences, the whole sentence. So word will be one. So all those have been converted into vectors. Because what is our machine going to learn? It is not going to learn the words. It is going to learn the pattern of those words in the form of vectors. So that is what we're doing. So this is the very important step of the algorithm, vectorizing. Okay. When we are vectorizing, we're converting it into array. Okay. Just understand that we are making a numerical representation. We are making a numerical representation of those, the whole sentence. Okay. The whole news wire. Now we are going to determine the number of classes. Again, we are going to convert it into one hot vector. So we discussed before also, right? How we are going to convert into one hot vectors by this two categorical. So we have imported this two categoricals again, like we did in this two categorical. Same way we are going to do here. So how do we know that? Okay, what are the number of classes here? So first of all, it is going to take how we actually know that what are the number of classes here. So we are going to use the data for that. The Y train. Okay. So the whole data is classified like this 0, 1, 2, 3, 4. Now there can be 23 categories. There can be 100 categories now. We don't know. Okay. Now we don't know how many types of news are there. So we are going to take the number of categories with the maximum value of the categories. Okay, so that is how it is classified 0, 1, 2, 3, 4, 5. These are the name of the categories can be different, but there has to be a number of categories, right? So that is how it is classified in. So if it is in the end, in the NumPy array, in the ND array, then it will show me this is the, or you can also say, okay, we have take the last index or anything. So this max Y train, I'm getting, okay, how many number of classes are there? Last on, if it is sorted, the last sequence, it will tell me, okay, this is our number of classes. I'm going to print the number of classes that we can understand it, because you see the amount of data that I'm actually downloading, I have no idea what it is. Okay. When you will also have a 10,000 or uh, 1 GB of data or something, a large data set, you will not have the insight. You cannot just see through your naked eye. Okay, okay. It will take a lot of time to understand what are the dimensions of the data. So you will use these things to understand the dimension of it. So there are 46 categories. So this is the number of classes. Now we are, and all those 46 will be now, it will be a vector of 46. All those y train and y test again are converted into one hot vectors, imported vectors. Now here we are going to create our neural network again. Here what we do, empty neural network. Here we create an input shape, how much input it should actually expect, and this is the activation function, and this is our number of neurons in the hidden layer. Again the dropout, again one hidden layer, in 0.5 dropout, and in dense I'm writing num classes because that is the number of categories we need. Now, when I'm creating an output, again, all the probabilities will be divided into 46, and we are making a summation of all those 46 probabilities. It should come to 1. So the maximum probability, whatever the category has the maximum probability, it will consider that as output. We are taking that activation as softmax. Now we have understood that what is RADO function. RADO function does. Okay, so I don't need to repeat. Now this is our neural network. Again, now here, again we are taking that categorical cross entropy. What we did in the experiment one, because we are in many number of categories. Optimizer is Adam itself. We have compiled our model. Model is ready. Now we have to, what we have to do is train. Now we have 20 epochs here because we want to train our data 20 times. Again and again and again. So increase the accuracy. The way the accuracy is increasing 0.18, 0.465662. More and more we are training, more and more our accuracy is increasing. The last epoch it is taking, okay, accuracy is loss is gradually. Sometimes it is a little bit of, but the loss function again, and we have that activation function. The learning rate and everything, considering everything. So this is the just a value loss. We have a function with the weights, adjusted weights and biases, but we don't know that what is actually working on that. Okay. What absolute value of weights and biases are being considered. So that is the hidden thing that this dot fit method is doing. Now here what we are doing, evaluating the model on the test set. Here we are going to get this 77%. That is a good accuracy, I would say. So 77% of times it will tell me, okay, you know the correct amount of, sorry, the correct category of our news. So what it belongs to, sports, you know, or the politics or the miscellaneous, whatever category. So we have seen 46 categories, right? I'm going to like list all that. You understood? So this will conclude our experiment 3, that was use classification, use category classification. Okay. So let's come to this. Design a neural network for predicting house prices using Boston housing price dataset. Now, this is a very famous problem, and you must have heard it before, that we are going to use the neural network using this. We are actually predicting the house prices. So we are going to use Boston housing price dataset. So basically, on you know using a number of categories, we are going to predict house prices. Obviously, it's a label data. And you must be wondering that why don't we just use linear regression for this? So we can use linear regression, but we might not get the absolute result that we are actually looking for, because the variables are around 10 to 12 or something. Okay, when we have that many dimensions, that means our data might be complex. So our neural networks actually works through that, and through that complex through that complex data, our neural network gives a better output. Just give me 1 minute. Yes. Okay. So now what we are going to do, we are going to build a neural network. So again, we are going to take the data sets from the KRS itself, TensorFlow KRS itself. Again, we are using the sequential, dense, and normalize. And the libraries are imported. And again, we are taking that data, training and test. It's already divided. Okay. Now we are doing normalization. X train, normalize, X train, access zero, access zero. Okay. Normalize means what? We are going to scale our input features between 0 to 1. I've explained before, but let us go through this again. So whatever we are going to, whatever input features we have, we are going to put in the category in between 0 and 1, whatever values. So it will be obviously a comparative. Some might get 0.1, some might get 0.9. Okay. So we can have different dimensions of input. Let's say something has the price is 40 lakhs. Okay, the acreage, the the area is 4,000 square feet. Let's say that's an example. So both have different units, and both have the 4,000 importance of 4,000 and 40 lakhs is different. But then we are actually making the, if we have to compare them on one scale, then we'll have to make the how how we are actually treating 40 lakhs and how we are actually treating 4,000. Okay. So based, and just giving an example that let's say the value of 5,000 square feet is 5 crores. The value of 4,000 square feet is 4 crores. Now, on a scale from 0 to 1, if I'm saying from a scale of 0 to 1, if I'm plotting this, you know, 4,000, it might plot 0.8. But when I'm plotting 40 lakhs compared to 55 crores, Now it will be 0.08. So you understand that this is how we I'm normalizing the data. Okay, so I am going to whatever might be the weightage or whatever might be the units of that, I'm going to normalize the data between 0 and 1. So basically, what is the importance of that unit? That is what it is showing. I've given you an example. So just understand. 50 lakhs is reduced to 0.08 based on the maximum of it, and 4,000 is 0.8 because the maximum of my area that we have is 5,000. So not necessarily maximum, it can be an average or anything. So we are basically normalizing our data between 0 to 1 based on the importance so that they would fit on a same scale. So it makes our neural network easier to understand that data. Okay. Again, here we are making our neural network. So what is this? We are creating empty neural network. Since, so I said we have 13 input features. All those input features will be, so our neural network will expect 13 input features. So again, here we have 64 neurons again. So here we don't have any drop or anything. We're not dropping any neurons in anything. Don't need that. Because actually we have limited. This is our input hidden layer, and then this is the output layer. So it is just going to give the house price, predict the house price. So let's say input feature neuron one. Input feature. So let me tell you how this input feature and neuron is going to behave. If there are 13 input features, all will go to neuron one. Okay. There are 13 input features, all will go to neuron two. Each of the neurons, all those 13 features will go. Now, when this is clear, our neural network is clear, our neural network is built. Now I'm going to build the model. Now, optimizer is Adam, the loss function is mean squared error. Okay, so it is a regression task, not a classification task, it's a regression task. So, what was mean squared error? Deflection. Okay, the deflection of that pricing from the actual pricing is the error. When we are talking about the whole data set, then we are taking the mean squared error. Okay, that is what. So when we are talking about the linear regression, that is what is used to check the accuracy of the project of the model. Our optimizer is Adam again, and loss function is mean. So our what is our target to minimize that loss? Okay, now we have created a compiled our model. Now I have to train our model. I have taken 100 epochs because it is going to take a lot of effort to learn. This is a regression task, and we want more and more accurate. Now you can see that value loss every time is decreasing. Loss is decreasing every time. That is what you want. Again, again, again. Now the final loss it was 36. That means uh, we are getting the means close to accurate price. Previous loss you can see it was mean square. The loss it was like this 582 or something. It was now from 582 we are through this learning. Our model is learning 100 times, and every time when it is predicting a wrong thing, loss function is adjusting it. The optimizer is sorry, not the loss function. The optimizer is adjusting it, the learning rate, and it is adjusting the weights and biases. And again, the weights and biases means what? The let's say if it it was a regression. We used to write the the slope and the constant. Okay, that is what it is. Every time it is adjusting the weights and biases, and it is creating a new equation. Again, that new equation is used to create a new output, and again, our loss is calculated. So that is how we are going to we are actually decreasing that loss. We have a loss of 36. This the average into loss of 9.25. Let's say this. What are the predicted prices? So now let's have a look. Predicted price 29, actual price 32.5, 21, 29.6. So you can see, okay, there sometimes there is a deflection by a lot, but you can say that almost in the most of these outputs, I'm getting almost correct price. Okay. So that is how we can say that, okay, our this model is might not be 100% perfect, but it is working properly. But because it also needs to, a lot of amount of data it needs, and we have used it for made it learn for 100 epochs. We might might be used. We can use for 200 epochs or 500 epochs. The more the merrier. But sometimes it won't, because the data, what is actually affecting uh, the prices, it could be, the learning could be limited by that. So you will never get. That is what I want to explain. You never get 100%, 100% accuracy. So you can get like 87% or something. That is a good accuracy. 85%, 90%. That is a good accuracy. Let's plot. We're going to plot predicted versus actual prices. This could be the perfect prediction. So this will conclude our four labs, lab 1 to lab 4. Are there any questions? We ask. There are none. So are there any questions? Here, ample amount of students here. Is there any doubt or anything you can ask? I'll take that as a no. Thank you very much. We'll have to take 6 labs. Everyone.